hi everyone. So I think this is a CSP seminar before the fall break, and it's our great pleasure to have David Inouye. Sorry,
that's good. That's good.
From ECE Purdue to give us a talk. And David is assistant professor at the Purdue ECE, and his work on trustworthy ML and causally inspired machine learning and domain adaptation, generalization, and his group is funded by DoD and NSF, and he also receives the NSF graduate fellowship during your PhD, right?
Mm-hmm.
So he obtained his PhD from UT Austin, and he did a postdoc at CMU. And today he will be talking something very interesting on domain counterfactual for explainability, fairness, and domain generalization. So with that, the room is yours.
Oh, thank you. Thank you so much for having me, hosting me here. It's been a great trip. I'm very excited to be here. And I'll hope this presentation, especially since we have a small group, feel free to ask questions if something doesn't make sense. Covering a fair bit of ground today, hopefully, but we'll see, including introducing a little bit of causality, enough for hopefully you to get the basic ideas. So this is work with a lot of my students, Zayu, Ruchi, Tianqi's actually Jing Gao's student, but we've worked with him, and Sean Kalinsky. Yaoji is a postdoc now at Georgia Tech. And Murat Kajolu is another. Jing and Murat are both faculty at Purdue. So this has been, all this work is, much of it is with collaborating with them. So very thankful to them. So first, domain counterfactuals. It asks this question: what would a sample look like if it had been generated in a different domain? So what would a cell image have looked like if it had been generated at a different hospital? What would a person's loan application look like if they were elderly rather than young? And what would maybe this wheat image look like if it had been in Germany rather than in France? So these are the kinds of counterfactual things that we kind of do all the time, and I'll formalize this a little bit more later. But domain counterfactuals could improve multiple areas of trustworthy ML. I'm interested in exploring this aspect. The first one I'll touch on is explaining distribution shifts. This kind of motivated the work of exploring this more. Then I'll talk about counterfactual fairness, recently accepted in NeurIPS, a specific type of fairness, and then domain generalization or outer distribution robustness. This one is under submission. I'm very excited about this one. These results are since last night, so you're the first to hear of these results, some of these results in regarding domain generalization. So I'll first go through 3 applications. These explaining distribution shifts, counterfactual fairness, domain generalization. And then the last part, I'll go through another paper we have on estimating domain counterfactuals. How do you actually estimate these just given data from the different domains? And it's both a hard problem and we can't provably recover it exactly, but we can do better than the naive thing. So starting with the first one, kind of briefly, why would you want to explain a distribution shift? First, what is a distribution shift, just in case you don't know? It's when the training distribution is different than the test distribution. So you train it on something and then you deploy it and it's a different distribution. It's well known that these can cause serious problems during deployment. Most prior works have focused on detecting a shift. So if you know there's a shift, you can retrain or do something about it. I realized I've talked to some people in the industry and they're like, we just retrain all the time because it's always shifting and we don't know how to deal with it. So we just retrain every day or every hour as fast as we possibly can, or at least costly as we can. So there is this question of, should we retrain? When should we retrain? It costs some to retrain. Should we ignore the shift? Should we gather better data, et cetera? Our goal is to aid the operator of an ML system in explaining how has the distribution changed from the training to like a new distribution. So we proposed three. This is more of a summary. We proposed three different kind of ways of doing it. If your features are interpretable, we kind of propose kind of a simple sparsity-based version or a cluster-based version. So you assume some structure on the map. If the map is sparse, meaning it only changes a few words, let's say, between two distributions, how do you map that? Cluster-based, you assume that the data is in clusters and the clusters shift together. Both of these heavily use some ideas from optimal transport theory, if you know too much about that. But basically, we used optimal transport, but then added some constraints to the problem to make it more interpretable. The second part was if the samples are interpretable, so if you're kind of in the image space and people can interpret, then on the left is kind of what you would see if I just saw samples from different hospitals. It's a little hard to tell what's different. If you actually make them counterfactuals, though, so I take original sample from hospital 1, and I see what would this have looked like in another hospital, you can clearly see the staining differences or color differences over different hospitals. But we were doing kind of, this last one was actually kind of what the motivation a little bit for studying counterfactuals more, because we were using the term counterfactual a bit naively. We were essentially using CycleGAN or StarGAN to do this translation. We didn't have a lot of theoretic backing for this. It was just an initial attempt. Our paper was kind of like, here's a problem. We're going to give you some methods to do it, but we're not claiming these are all perfect yet or anything. So this previous idea just relied on the inductive bias of GAN-based models, probably based on convolutional neural networks have a bias towards texture and things like that. But there wasn't any like theoretic reason why these should be the correct counterfactuals. So the rest of this presentation actually will be more on theoretically grounding the idea of a counterfactual. What does that actually mean? What are the mathematics for that? And how do we use that for counterfactual fairness and domain generalization, as we'll talk about next. So what is counterfactual fairness? It requires, the definition requires that the same predictions across different counterfactual worlds. So it means that even if we intervene on some attribute, so rich versus poor in this little illustration here, let's suppose there's this law school admission for fictional characters. Aladdin is poor, is predicted to have a 50% chance to pass the bar. What would have been the model's prediction if Aladdin was instead rich? Would he have, passed it or not? If the predictions are the same, meaning we give the same prediction to these two different Aladdins, one who's the factual poor Aladdin and one is this rich counterfactual Aladdin. If we gave the same score to both of these, then and do this for all possible people, let's say, then we kind of say that our model is counterfactually fair. Otherwise, it's not. So you might be able to like get this question, understand conceptually, okay, hypothesize about this person having a different kind of some sort of different attribute, and what would their life have looked like if that attribute was different. But we actually need to formalize what we mean by this counterfactual. So hopefully this will motivate the idea that we want this kind of thing for this fairness, type of fairness, and then kind of use it from there. So here's some background, very, very short primer, hopefully, on causality. So I view, this is partly my take, that causality is basically probability plus this notion of intervention. Intervention, somewhat generically, and I'll talk about a specific example what I mean by intervention. I don't think you can't get at causality with just probability. You need this other concept called intervention. Even if you don't actually do an intervention, you need the concept of an intervention to get to causality. So probability alone cannot answer certain questions about causality. So for example, the use of umbrellas and rain are highly correlated, right? When it's raining outside, people use umbrellas. When there's a lot of umbrellas outside, it's probably raining, right? They're very predictive of each other. They have a very strong statistical dependency. You can, if I tell you there's 100, there's 1,000 umbrellas on Michigan's campus, then it's probably raining, right? If I tell you it's raining, then people are probably using umbrellas, right? Okay. And it's all great. But do umbrellas cause rain? Or does rain cause umbrellas? So probability theory cannot help us with this part, right? We just observed that every time we see umbrellas, we see rain, and every time we see rain, we see umbrellas. There's nothing about this distribution that can actually answer this question. So this is where interventions come to the rescue, and the notion of interventions is very important. So if I intervene, if I force everybody to take an umbrella, and use an umbrella, everybody on Michigan's campus, say, everyone, you have to use an umbrella today, right? That's an intervention on what their normal behavior would have been. But I force everyone to take an umbrella, does it start raining? Hopefully your answer is no, it probably wouldn't start raining. Everybody would just have umbrellas on a dry day. On the other hand, if I put fire hydrants up and I spray water, so it's essentially simulating rain all over University of Michigan's campus, then likely people will start using umbrellas. Right? So there's one direction which causes the other. And by this notion of intervention, again, it doesn't necessarily have to mean you actually do this in the real world, but you need this concept of intervention to get at causality.
Can you get by with temporal sequence of events? Because information typically doesn't flow backward in time.
So yeah, like the kind of Granger causality.
Yeah, just watch what happens in the world, and if the rain starts before the umbrellas, that's one thing, and if the umbrellas start before the rain, that's another thing. Doesn't work very well with smart people who predict, right?
Right. So I've looked into this a little bit, and I think you end up getting more forecastability, but not causality from that. So it's still more predictability, but now it's a predictability in time. And even I think Granger, who it's named after, whatever, was kind of like, this isn't exactly causality because it doesn't have this notion of intervention. Because you can have things like, suppose there's a cause and then there's two events, it causes two things that are delayed, but they're slightly different.
Yeah.
So then you can't reason as well about like confounding effects.
I bought it before I asked. I just
Oh.
wanted to see what you say. I'm
Sure.
curious what you thought about that.
Sure. Yeah, it's a great question. Yeah. I think even when you're reasoning over time, you still need a notion of intervention to get at something interesting in causal space. Again, is predictability enough for your application? Well, that's kind of an application question, but if I want it to rain more, I'm not going to sell a bunch more umbrellas or give a bunch of people umbrellas, right? Okay, now we're going to talk about structural causal model. So now we're going to, again, the intervention is the key idea that we need to have for causality. And SCM's kind of formalized this mathematically. What do we actually mean by this? So we're going to assume each causal variable is a deterministic function of its causal parents and some exogenous noise. So some extra randomness that is not modeled by anything else. Okay. So it's a deterministic function f. It takes in its parents and it takes in some extra noise. Here's a simple example. So at x1, some exogenous noise epsilon1 is equal to 2 epsilon 1. So as you can see, it's just a deterministic function that also takes in some noise for each variable. So you can think of these as exogenous noise, but then kind of the causal variables you care about are here in blue. And they are deterministic functions of their parents. So x3 has parents of x2 and x1, and also epsilon 3. An intervened structural causal model. So again, what do we mean by intervention? We mean we change one of these functions. We might keep the other functions the same. So in this example, I kept f1 and f3. They're the same functions. I just changed the functional form of f2. So I changed what happened here. Now, the most common case when people talk about interventions is to set this to a constant. Forcing everybody to smoke or forcing everybody to not smoke, or giving them a treatment or whatnot. But you can think of it more broadly as change one of these mechanisms. And in this case, I changed it from x1 to x1 squared, and that would change the model. So this is what we mean by intervention. Now, counterfactuals bridge two causal worlds. So we had the non-intervened and the intervened causal world in the last example. And counterfactuals bridge between these two. They're kind of this weird thing because they consider the distribution of variables in one world given evidence in another world. So you need to be able to jump between these two worlds. And how do you do that? Here, I'm going to use a little illustration. So the usual way to form these counterfactuals is I'm given some evidence. So this is some data in the factual world, which I'm going to usually denote by this orange color. So this is, you could think of as factual data. The real latent was poor. Now I'm going to infer this exogenous noise, this epsilon 1, 2, and epsilon 3. Now in this case, this is invertible, so I can actually recover the exact values of epsilon 1, 2, and 3. If it's not invertible, then you have to do some sort of posterior estimation. So you kind of estimate the distribution of epsilons. Now you do action where you change the world. I move to a new world, and I set the same exogenous noise in the real world and the counterfactual world. So I go from the poor epsilon, and I make the rich epsilon equal to the poor epsilon, and then I run through the causal model again. So now I run, but I do remember that this down here was a different function than it was up here in the previous world, okay? But all the other functions were the same. And as you can see, this should have been a 2. Sorry. Because epsilon 1 was 1, so 2 times 1. So 2 would have stayed the same. And then x2 changes and x3 changes. Okay, because I intervened only on x2. But it had cascading effects on x3 because I just changed that one function, but that was going to be used in another function, so it had a cascading effect. So now we have the counterfactual latent in a different world where he was rich. Okay, so that's the counterfactual is, you kind of go back to this noise, you switch worlds, and then go forward through the generative process. That's how you get counterfactuals. Our structural causal model, specifically for fairness, assumes an unobserved but invertible confounder. So we're going to have this latent confounder between x and y. So suppose the input is something like your GPA, your target variable that you're trying to predict is, will this person pass the bar exam? There's some sort of confounder that, for example, is like the stability of their home life, right? That if they have a very stable home life, they're more likely to have a higher GPA and they're more likely to pass the bar exam. So there might be a confounder between these. And then some sensitive attribute, age or race, where you're trying to say, I don't want to discriminate against different ages or different races. And the prediction is based on A and X. I can use both of them to make my final prediction because I observed them. In intervening on A, so we're going to be considering the idea of what if I took someone's age and changed it counterfactually? What would their prediction have been in that case? And that, so that can intervening on A affects both X and Y. So it can either be indirectly through X or directly through Y, but we're allowing this A variable to be a parent of both X and Y. Okay, again, to be fair, what we want to be is that given a factual A and X, what if I switched A to be A prime and did our counterfactual like we did before, like changing my latent from rich to poor? Would they have the same prediction? So how do we measure that? This maybe reinforces the point. Total effect measures the expected difference between that factual and counterfactual predictions. So more formally, what does a predictor mean to be counterfactually fair? If the prediction, the distribution of y hat, given the factual xa and x and a, is equal to the distribution of the counterfactual prediction. So this subscript is how causal people usually denote a type of intervention. So instead of being A, I'm going to counterfactually change to the other A. In this case, A is binary, so that's 1 minus A, given the evidence of the factual. So let me illustrate what that looks like. So the prediction on the poor latent, that's factual, given the original factual latent, is that prediction the same as the counterfactual latent, where I got that counterfactual based on the evidence of the factual. Right? So I want these predictions to be the same. So roughly we can measure that between the factual prediction and the counterfactual prediction, where the counterfactual prediction uses, switches the attribute. And you can write it like this. This is the total effect, kind of a measure for how unfair something is. If this is 0, then the predictor is fair. Otherwise, it's unfair.
P is probability.
What?
What is P?
Yeah, representing the distribution of y, so the class probabilities. Yeah. So the counterfactual problem is, you want to minimize some sort of risk. You want to be able to predict y well, but you have this constraint that I want it to be counterfactually fair. I want this total effect, which measures fairness, to be 0 so that it's fair. So what we actually showed, this is kind of one of the main results, is that the optimal counterfactually fair classifier simply mixes the factual and counterfactual predictions. So in a sense, to theoretically solve this problem, the optimal thing to do, their optimal counterfactually fair, basically the best possible risk you can get under the constraint of this counterfactual fairness is actually fairly simple. You mix a simple mixture based on the prior probabilities, where this phi star is without the constraint. So this is like the Bayes optimal classifier, ignoring fairness. So I take an unfair classifier, this Bayes optimal classifier, and I mix it. I mix the distribution, like the prediction of XA and the prediction of the counterfactual. And we basically prove that this is actually optimal in terms of risk, given that constraint. And the excess risk is the mutual information between A and Y, given U here. U is that unobserved latent confounder. If you've done a lot of fairness before, this is a similar result for demographic parity, except it's not conditional on U. And so it's kind of an analogous result. It's actually kind of counterfactual fairness is a much stronger condition than demographic parity. So if this mutual information is maximal, A and Y can't really be disentangled at all, and therefore you're going to have a lot more risk if you force it to be fair. On the other hand, if the mutual information given U is 0, then the kind of original ERM type of classifier is already fair, and so you don't lose any accuracy. So this kind of helps show the trade-off between fair and unfair classifiers, because there's always accuracy. Fairness is trade-off is a common thing in fairness. So let me give you a little intuition of what this looks like. So the unfair optimal classifier could achieve 100% accuracy on this. Even a linear classifier, basically, right? You just put a line here, and even the unfair classifier will do well here, right? And the two domains, so this is the x's are one domain, and then the dots are another domain, and classes by color. Now, if you look at the counterfactuals in this example, the counterfactuals are essentially just move across this line. So I've drawn them in these gray lines show the counterfactual. This point is a counterfactual to this point. And you need these to have the same value to be fair. So each endpoint of these gray lines needs to be the same. So what can you do? Well, on the points where they disagree, right, where they're giving different predictions, then you just have to mix them. That's the best you can do. So in this case, give it kind of a purple probability. And now, again, let me use it better. Every point has a corresponding, the counterfactuals are across, kind of moving between counterfactual worlds is just to jump across this direction. And so you want all pairs of points to have the same color. And now you do, because you mix them. So that's the basic intuition. Obviously, now you're going to incur some error in the purple region. That's where you're kind of going to incur some excess risk in comparison to an unfair classifier. But now you're fair.
Is PA known?
What?
In the formula, there's PA, right? In the optimal, there's PA and P, like 1 minus A. Is that quantity known or?
I think like in this simple example, that like PA and P1 minus A are equal, so they're 1/2 each. So you just average. But if one of these, like there was a lot more X's, then you would adjust for that with those.
I thought A is unobserved.
So in fairness, sometimes A is observed, sometimes it's not. In our case, we assume it's observed. I think you can generalize this result to so there's also a question of, do you observe it during test, train, or test, or both? I think in our case, we assume you observe it in both. But I think you can get a little bit similar results if you assume you only observe it in test. I mean, only observe it in train. So we apply this basic idea in practice. Basically, this is just comparing to some other methods, and we get a better trade-off. Our curves on the bottom of the unfairness and the root mean squared error in this example. So we basically just take, we learn a simple ERM type classifier, and then we just mix the counterfactuals. And this will empirically be able to give a better trade-off between fairness and accuracy. Okay, so that was counterfactual fairness. Now I'm moving on to domain generalization. This is hot off the press again. This was like last night, working rigorously to get it ready for submission. So you're the first to know about some of this work. or the more recent results. So let's first talk about domain generalization, in case you're not familiar with it. It aims to predict accurately even under some distribution shift. This is a well-known real-world distribution shift data set that has training examples and test examples in a different domain, multiple domains. For example, I have multiple cameras looking at animals, and they're a little bit different. Some of them are grayscale. Some of them are closer or farther from the animals. But you have some domains data for training, and you want to generalize well to these test domains. That's kind of the core idea. It's a type, I would call it also a specific type of out of distribution generalization. Instead of in distribution generalization, which has been kind of the focus of more classic machine learning, out of distribution is kind of the new thing that we're trying to do. The problem is that simple ERM often wins. If you just tune the parameters right for ERM, it's hard to beat for domain generalization. We found this in our paper when we did federated domain generalization. It was very hard to beat the simple federated averaging algorithm, which is essentially the ERM equivalent in the federated space. So perhaps this problem setup is actually just too hard. Some people have conjectured this. Maybe it's kind of an ill-posed problem. Maybe it's kind of like an extrapolation. But extrapolation is hard unless it's like linear, right? If it's linear, you can do extrapolation well. But like if you don't assume anything about the function, it's impossible. Maybe if you assume some smoothness, you can get a little bit better. But extrapolation in general is very hard when you don't have that kind of data. So what is the value of different kinds of data? So people have tried to relax this problem a little bit. Maybe this is too hard. One way is to add some labeled test domain samples, right? This seems like a great idea, but then it's not really domain generalization anymore. This might in practice be a good way to get around a lot of problems. Like if you're, just get some data and label it. Another weaker approach maybe is to get some unlabeled test domain samples. So this makes a little bit more sense. So suppose I deploy a new camera in the wild. It's going to look different than the other cameras that I've already deployed and that I have labels for. But if it's connected to the internet and sending me data, I can get unlabeled samples from this new camera. So in certain cases, getting unlabeled test samples definitely makes sense. And so this can be multi-source domain. This actually turns it into more a domain adaptation problem. But it does require adapting to each new test domain. Like we're not actually making a model that's actually robust to like any new test domain. It's robust. It only has to be kind of fixed every time or adjusted for new test domains. So our proposal is to add kind of a data-centric view of the world, again, is to add a counterfactual pairs within the training domains. If we add these counterfactual pairs to the data set, we can do some other things. And we're going to show a very kind of simple algorithm to use it and prove that it actually can be really useful, actually. So in this case, you don't need any test domain data. So you only have data within test domains, within training. But you do need a counterfactual pair. I need the same cat indoors and outdoors. I can't have a different cat outdoors. I need the same cat indoors and outdoors or something like that.
So you have to know some properties of the test domain, the reason that it's out of distribution in order to generate those pairs or not? You need to know what outdoors means if you want to have your indoor training system work on. Okay.
Right. But what we're actually suggesting is that eventually we'd like to say, okay, you give me, let's use, we need more than two. So let's say, in the grass, in a forest, in a desert. So you give me the cat in grass and in forest, and I could generalize to the desert. So you don't need to know necessarily the characteristics of the desert domain, but so within the training domains that you have, you want to be able to make a pair within that. So you do need, some knowledge of what the domain means to maybe create these. So we've actually kind of thought about like, how could you create these? A couple simple examples is like for images, obviously you can Photoshop them. I mean, that's, you know, it might take an artist some effort, but in theory, they could Photoshop and say, you know, this is what it should look like in it.
You can maybe use diffusion models using text prompt to generate some background.
Yes. Yeah.
Like this.
So it might be possible to use foundation models to make approximate counterfactual pairs. I think what's interesting is that it's up to the kind of application expert to decide what are the counterfactuals that they care about. The nice thing is often domain experts would, or at least I conjecture, I haven't worked with any yet, but my conjecture is it's easier for them to, you know, if you go to a domain expert and you say, write down the mathematical formal structure of the constraints on your problem. It's very hard for most, you know, anybody really to write down formal mathematical constraints on their problem. But then you just tell me, give me a counterfactual, like, you know, here's an image. What are some perturbations where it won't change the thing you care about, right? So like for medical images, maybe, you know, often they have like, say, a cord on them. This was a common thing in COVID. Like people who had pneumonia already have some sort of lanyard thing because they're in the hospital and they have an IV drip or something. And so when you take an X-ray, of course, a human ignores that because they know that's an IV drip or whatever. But the model would pick that up and say, oh, this person is more likely to have it. Well, it's actually just a spurious correlation because they're in the hospital because they're sick or something like that. And so maybe a domain expert could say, oh, no, I'll give you an image without, or I can even take an image without that in it. I can tell the person to have it with it, and then I can take it out, and I can get two images where one has the spurious thing and one doesn't. But we can talk a little bit more later about how you could possibly get these or elicit these or create these. But our idea is, what if you could? What can you do with it if you had this data? Okay. We show that you can actually generalize to certain particular shifts, as we'll explain what I mean. And you only need a small number of pairs. That's the other big thing. Like if you needed like 1 million of these, it was, you know, they could be costly to get, but the idea is you only actually need a small number. And I'll show a little bit why this could be possible. So let's narrow the focus a little bit. I'm going to give you specifically what kind of model we're looking at and the assumptions that we're making. First assumption, the intervened variables between domains are not ancestors of the target variable. That's kind of the formal definition, but it ultimately means something like we only intervene on spurious features. So we haven't yet considered the case of what happens if you know, intervene on the thing that matters. Like I change the environment so I see more fish than I see dogs. Here I'm saying you're intervening on something that doesn't is spuriously correlated, not actually causally related. So we're going to assume that, and most domain generalization things are there. The core problem is something like there is some spurious correlation, and that's why you can't be robust. So that's one core assumption we're making. So
may I ask a little bit on that? So in the cases of those spurious correlations, is it because there's something else that's causal for the spurious correlation, but also causal for the thing you're deciding?
yes.
Or because the arrow's in the wrong direction and the thing you're looking at actually causes which?
Right. So spurious correlation. So in this example, Z2 here is the single parent of Y. Yep. It has an ancestor. So Z2 has a parent himself, Z1. So all these green things are the ancestors. Mm-hmm. So we're saying you can only intervene on non-ancestors, which are any of these.
Okay, yeah, that answers it. Yep.
Yeah, and spurious, this one is spuriously correlated. This one actually is just independent.
Yeah.
But this one, if you can see, right?
If you got arrows going over the left there, yeah.
So you know, you have this confounding effect where these are correlated because they both have a common ancestor. Yeah. We're also assuming, this is also another fairly big assumption, but I think it's a good starting place. That the new domain, the new test domain, can only intervene on the things that the training domain did and any descendants. So we're making an assumption, you can't say the new test domain like can't intervene over here, and it can't intervene on say Z3 because we didn't see that intervention in the training domains. Now, note that all of this is latent. All this whole space up here is latent, so we don't, when I say we make these assumptions, we can't necessarily check whether these assumptions hold. A domain expert in some sense would need to tell us whether these assumptions hold by looking probably at counterfactual, examples and saying, yes, there should be a difference, or no, this should not have an effect on the prediction of the label. But all this is latent up here. The Z's are all latent. We only observe X and Y. And then assumption 3, we're going to do a linear structural causal model. We hope to extend to nonlinear at some point, but for now we're going to deal with a relatively simple linear one. But it's still latent. So you have this exogenous noise distribution. Your Z are just some linear function of UZ. Okay, you could have a shift term like a translation term too, but we're just going to simplify it to that notationally. And then to get from Z to X, we have just another linear combination of Z's gets us to X, gives us to our observation X, plus possibly some other exogenous noise, UX. And then Y is some function of the original Z's. So it's just an inner product here for a simple binary type of classification. So Y is also a linear function of Z. Okay, that's also visualized here in the graphical model. Okay, so these are our 3 main assumptions. So here's the simple problem we're going to set up. We're going to do ERM plus a constraint. So this is the constraint is based on the counterfactual pairs that we have. I have some data from the training domains, and I have these counterfactual pairs. I have two sets of data. I'm going to train on the normal training data up here. And here I'm going to say that I just want the predictions on the factual and the counterfactual to be the same. This is actually very similar to the fairness constraint. Okay, we're just making kind of different causal assumptions and stuff, but the idea, we want these to be the same. So can the classifier that we learned doing this generalize to new domains? Very simple idea. I want to go through a little example to kind of give you the core intuition why this might be possible. So here's an example. We have these two training domains. We have one counterfactual pair, only one. In this case, illustrated by green here. The shape denotes the domain, and the color, purple versus orange, denotes the class. So an ERM classifier would be something around this. The C hat that you would have points in that direction. Okay. However, now I look at the test domain. It's just one example of a test domain in the pluses here. As you can see clearly, this would get very bad accuracy on the test domain. It got really good accuracy, but now the red is being classified as purple and the purple is being classified as orange, or I guess it's orange, sorry. So this would get like almost, you can make this so it could be arbitrarily bad classification essentially here. So now let's look at what would our counterfactual matching type of problem would do. So I want the constraint here is that I want these to be equal. So in the linear case, this simplifies to C transpose the difference between the counterfactuals, which is illustrated by that green line here. So this difference, right, is this direction here, right? I want my C star to be orthogonal to this counterfactual. So by making it orthogonal to that subspace that was spanned by this counterfactual, I actually get the robust classifier. Again, you don't have access to the test data here. You're just using the training domain data, doing ERM with that, plus this constraint that I need to be orthogonal to this difference vector between the counterfactuals. This is the core intuition. And kind of the basic idea here too is this shows the few shot idea that, obviously in higher dimensions, if you get each counterfactual pair, assuming they aren't linearly, dependent, if they're linearly independent, they start spanning a space that's a k-dimensional subspace and say, I want my classifier to be orthogonal to that k-dimensional subspace.
Would be a counterfactual pair for the test domain, although the conceptual, although we don't have access to that, but what would be?
Right, so the counterfactual pair in the test domain would look like this to this. It would also be in the same direction.
And that's why it allows us to generalize and see test.
Right, because it essentially allows us to identify the spurious feature space. It almost seems too simple once you look at it. But what's interesting, of course, is you started with this counterfactual that people might have a way to reason about semantically in their domain, and you get somehow this kind of nice robustness property that this, again, the constraint is specified by data, specified by these counterfactuals. But by doing that, you can implicitly learn the space that you want to be orthogonal to and get this robust classifier. All right.
That makes sense.
Great. Now in practice, so that was the clean, really nice, suppose you have a perfect counterfactual. That was to give you the intuition of, you're essentially these counterfactuals implicitly define the spurious subspace. Basic idea, if we want it to be, if we have noisy or approximate counterfactuals, so even if we don't have perfect counterfactuals, we basically use an idea of, we'll find the best rank R subspace and make it orthogonal to that. So we can write this like this. So I take, a bunch of samples, then I take the differences between the counterfactuals for each pair. And so we're mostly dealing with this delta matrix. I use the tilde to denote the noisy version because there's like the ideal version without the tilde and the noisy version X tilde. So this is a noisy counterfactual. So instead of it being exactly like, like it was in the previous example, maybe it's like this or like this, something like that, right? It's no longer exactly in the right direction, but then the natural thing is to actually use, find this subspace, this from noisy estimates of it. So we're just going to use simple,
What is the size of the subspace?
R.
Yeah.
Yeah, that one's still thinking about it. I mean, R, ideally you would set R to the number of spurious features, but you don't necessarily know the number of spurious features that were intervened. So it could be, there's a trade-off between if you increase R, you're reducing the set of possible classifiers because you want to be orthogonal to that space. So you're reducing the set of possible Cs. On the other hand, if you don't use any, if R is really small, then you're not removing spurious features. So you probably want to do, you could either have like a held out test domain, held out domain, and use that to kind of tune R in practice. To say, you know, which R will give me robustness, but also accuracy, right? Good robustness on the new test domain. But I have to say, we're still kind of contemplating what's a good way to choose, in practice, to choose R. And then here's the theorem that was last night. We were pulling it together. This probably looks crazy, but I'll try to walk through it very briefly and just kind of highlight the main things. So the test risk on the new test domain is less than, this is the training domain risk. So obviously we're minimizing that. You can bound that by an ERM to population level risk type of bounds for term one. Term two is, this is the like best possible robust classifier compared to the true value. If the true, well, this is actually an regression setting, sorry. So this is like linear regression with mean squared error. That's why there's all these squared terms. So this is like the best possible risk you could get, you know, with Oracle type knowledge. And if there does exist something that equals Y, then this would be 0. That's inherent to the problem. You can't reduce that term. But then there's this term 3. This one's due to basically, we have a set of counterfactuals, and you can think about what's the kind of covariance matrix of this set of the difference matrix, that delta. You can think of that as samples of deltas, and the covariance matrix of that. This term deals with, well, we're using in kind of an empirical covariance matrix instead of the population level, and so there's concentration bounds on that. That's term 3. Term 4, this one's probably the most interesting. This is based on the recovery of subspace. So how bad is your subspace when it's noisy? So when you have some sort of noisy, but you want to recover some subspace, there's it's called this Davis-Kahan type of theorem that shows what, you know, how close can you get to the true subspace that you care about. So people have used this in like PCA, right? If you have noisy measurements, you're still trying to recover a subspace. How close do you get? That's where this bound comes into play.
What are the math cal O's? Sorry, I just don't follow.
Oh, these are just like small constants. Yeah, it's small constants. I think these were like 2 or 4 or something like that.
Oh, so it really is order rotation. Okay.
Yeah.
Fine. Yeah.
Yeah. So if you look at this particular part of the bound, right, this part right here, this is kind of the comparing the true covariance to the empirical covariance, like how much perturbation there was. So it obviously depends on how good more noisy your counterfactuals get, the worse you're going to get. This has to do with the gap between the eigenvalues. So there's you need a big gap if you want to recover this K top subspace. You need a fairly large gap between the eigenvalues if you want to get good recovery. If it's really close, it's hard to ensure that you recover the right subspace because they could be perturbed near each other. Those are probably the kind of the core main terms to this part of the bound.
Here, how does this sample number of few short comes into play into this setting?
So that's gonna have to do, I think.
So your subspace is low, rank R is very small, you don't need so much samples to estimate subspace.
Good question. I feel like that might have to do with, so K here is the number of samples, the number of counterfactuals, sorry. This is the number of counterfactuals, M is the dimension of the space. So you see K come up here and here. So I think it roughly decreases this 1 over K in terms of these parts.
So what is M?
M,
M.
the dimension of the space.
But if the K needs to be larger than M, seems. But in the feature space, you could like have some dimension reduction. The feature would be already low dimension.
Right, right.
Might be.
We're not doing any special, I guess in some ways, we're not doing anything new techniques here. These are all standard techniques for doing these kinds of bound, I think. But I also haven't had time to like really think about each term in this bound yet. So love to discuss more if you have thoughts. And then, does this actually work in practice? So, or like, is this even feasible? It's kind of an open question. So we had some results on synthetic data that use, this is just a simple example. I think this was on, I think this might have been on rotated MNIST. I'm not 100% sure. But basically ERM given even the latent value Z and this is invariant risk minimization, all on the test domain were pretty low. Whereas if we did full counterfactual matching, we were able to do this. I think we had a lot of counterfactual matching, but here was the few shot example in the case of linear. So if the number of intervened variables was 20, then you need 20 counterfactual pairs before you can reach kind of the oracle amount of performance, right? But and same thing, if you had 40, in this case, 50 intervened nodes, then you need a little over 50 to actually get to that oracle case. But again, this is showing kind of the few shot. This is a simulated case, which kind of follows our theory that you only need. And I think this might even be the noiseless case, not the noisy counterfactual case. So this is with perfect counterfactuals, showing that you can actually do this in practice. And then finally, we did a little example on higher dimensional data, not exactly realistic, but simulated realistic. This is called the Waterbirds data set. I don't know. We kind of slightly modified the original Waterbirds data set. The original Waterbirds data set is you have kind of context and the label. So this is a water bird on a water background. This is a land bird on a land background. We created essentially some, and basically the problem is, how do you generalize a water bird on land background when you switch them, right? You don't usually see water birds on land or land birds on water, right? So you often, there's a spurious correlation between the background and the bird and kind of the bird type. So that's, at that test, there's kind of the cross domain versions of these. So it's kind of a semi-synthetic constructed example showing the spurious correlation. People have used this for domain generalization. And we just essentially added this, some counterfactual pairs, in this case, 240 of them. So you see the same bird in, two different locations. And here we can show that basically in comparison to ERM, particularly looking at this worst group accuracy, we're able to outperform ERM by almost 10%. And even after you kind of adjust for class weighting, which is this upweighting idea, which does better, we're still able to improve 3 to 4% over that kind of baseline, along with this IRM and group DRO other methods. And we show that it's actually a lot more stable than some of these down here is IRM and group DRO. So they do initially pretty well, like they kind of do kind of well, but then if you keep training them, they get really bad. Whereas ours kind of is stable like ERM, just kind of keeps going up and then stays there. So these objectives might be more complicated to optimize. The previous ones, ours is a pretty simple objective. So we kind of like that result too.
So the overfit to
yeah,
you can do early stopping.
Right. So that's actually the results we report here, I think, is early stopping at the top here. But that's still going to be under ours.
Okay.
But we're just also showing that in terms of stability, it kind of You kind of have to stop very carefully, otherwise it won't work.
Is there a class in here now or not? There's some people in the hall.
Oh, is there a class at 4:30?
Maybe there isn't. Who's the host?
Me.
Is there a class now or not?
Oh, I don't know. Usually stops as
I'll check with them. Please carry on. Sorry about that.
maybe it's our break.
Last class.
No, you're good.
Okay,
Please carry on.
okay.
In the class, maybe cancel.
So can the theory be extended, open question, to nonlinear invertible causal models? I think one simple case is, of course, use a feature extractor, and then apply this to that. That seems very obvious, and if we could do it, it still could have nice properties. The other big one is, how do we elicit these approximate counterfactuals in practice from domain experts, or just from in different applications? Can we actually create things like this? I conjecture we can, but we haven't kind of thought really deeply about it yet. And my hypothesis long term is that these domain counterfactuals provide this data-driven way to implicitly specify task constraints on a problem, right? Ways, just like class labels provided an implicit way of defining a task, this could possibly be a way to implicitly define constraints on your learning problem. So now, instead of saying, hey, write down mathematically what the constraints are on the problem you have, you'd be like, just give me as many counterfactuals as you can think of.
So this is a classification problem. I think in some cases you also want to solve some detection problems, like more like a binary detecting certain object, the existence, and they might be in different domains. And it could be like the object in the desert is the object is in different background.
So in any cases where you can come up with these counterfactuals, especially if you could, in certain cases you could auto-generate them. That's like data augmentation. So we'd actually think data augmentation is kind of an adjacent idea. So it's is this supposed to end at 4:30?
Yeah, but I think there's no class. Feel free.
Oh. Yeah, so feel free to go. I will try to be quick on this. I don't know, but I think it's also interesting. So we'll just go. Feel free to leave though if you need to go. So now we're thinking about, so there's the applications. We're gonna think about estimating these counterfactuals. How do you estimate these counterfactuals? Could you estimate them from domain data? We're gonna assume this causal model, kind of similar to before. We're gonna have the exogenous noise. We're gonna have some deterministic function f that goes to z, and then some mixing function g. They're both invertible in this case, so we're gonna make an invertibility assumption. Commonly, it's linear and then invertible, and then non-invertible becomes even potentially harder. So what does a counterfactual mean in this case? The factual latent was poor. I'm going to invert to get back the z's. Then I'm going to invert f to get back my epsilons. Then I'm going to transfer my epsilons and forward it through. I'm going to change f. So the f's are different, but this mixing function is the same. Okay, so ultimately, in this invertible model, I can actually just write it as a composition of functions, which is kind of nice. So how do you estimate domain counterfactuals if you're only given samples from the domain? So if you were given counterfactual pairs, like if you're actually given paired data, then you could just train a supervised model, right? Just predict, go from the cylinder to sphere domains. I just use my paired data and just treat one as the sphere as y and the cylinder as x. But what if you only have just domain data? You have a bunch of cylinders and a bunch of spheres, right? From two different domains. Is there a way to learn a good mapping between these two? I'll say basically there's two lines of thought. One is this is community. They think very carefully. I really like the way they think deeply about the problem. But often their assumptions are unrealistic. Machine learning community, they just, train the best model and hope it works. For example, maybe train a conditional VAE and assume that this recovers the things you care about. But I think this actually ignores some of the core challenges. It doesn't actually work really well in practice. So we're trying to bridge the gap between these two communities. So our theory supports 3 claims. First, you don't actually need to recover these ground truth F star and G star to get counterfactuals. So, we could assume this model, but we don't actually need to recover that. We can work on a simpler problem, like kind of solve a simpler problem rather than fully recovering these. So some of the recent work has been about actually recovering these, but you usually have to make really strong assumptions. Can we do it without actually directly recovering these? We can bound the error. We can't get it to 0, even theoretically, but we can bound it by 2 terms. Distribution fit, does the generative model fit the data? That's the easy one. And then reasoning about this intervention sparsity, this is an assumption we make. Causality often is, the importance of causality is often in which assumptions do you make and making them explicit. A lot of machine learning has tons of implicit assumptions that they don't tell you, and then you have no idea if it's going to work and it's something new. So part of it is to try to make explicit what is often implicit. So we say that we can actually bound this. This is one of our core theoretic results. And another result shows us that we can actually, because in the latent space, you can rearrange things, kind of like you can assume that the intervened variables are all at the end of your latent variables. So you can assume, it's not obvious that you can do this because in maybe the ground truth causal model, Z1 was intervened, but none of the others. But we show that you can do some swapping and get an equivalent model that will give you the same counterfactuals, but now where the intervened variable is at the bottom. So this is kind of practically helpful because you can design an algorithm with that assumption in mind. The error we bound here, this is our core in terms of result, is here's different intervention sparsities, so a different amount of variables you assume were intervened. This is the set of models that are distributionally equivalent. They have the same distribution as the data. We want to get into this set here. We can't, once we get into this set, we can enforce this using kind of standard maximum likelihood, and we can enforce this by a structural constraint on our model. But we can't actually determine any better than inside of this region here. So we might not get the ground truth thing. So we bound it. We say, okay, our original, whatever model we find is less than our best projection onto this set, then goes to here. And then we say, well, this C here is bounded by the kind of maximum distance within this set. That's the high level intuition. And that's how we get basically B plus D as our kind of bound. I'm not going to obviously go to the paper if you want what it actually is. But in practice, we learn a VAE with maximum likelihood. Very simple. Like this is a standard VAE type of loss, except we do this constraint. So we add a constraint to the problem where we say everything, all of these variables up here, the first, say, m minus k variables, all have to be equal between the domains. And I'm only going to allow the orange part here to be different. So only the last couple variables. So I'm going to be learning, I'm going to train with a bunch of spheres and a bunch of cylinders. And I'm going to say, you essentially have to model the same distribution, except I'm going to give you just a little bit of flexibility where I can generate spheres or I can generate cylinders. But otherwise, everything else has to be the same. So the rest of the parameters are shared, and only just a little bit of these last 2 dimensions are kind of domain specific. Everything else is not domain specific. And then in practice, what do? You use the encoder for your factual, let's say the cylinder. I take the noise I receive here. I do basically like what you did in the counterfactual. You switch worlds. I now switch to the sphere world. I use the same epsilon. I forward with, now there's a new d prime. This is in the sphere world. I'm going to decode with the sphere world. Okay. So that's where the counterfactual happens.
Is that the main reason you need the invertibility assumption?
The invertibility is mostly mathematically convenient for the proofs. So in this case, right, it's a kind of pseudo-invertible VAE. So in practice, you don't necessarily need it. But in the proof, it's hard to show certain kinds of properties. But it's easier when you can have invert stuff and say, oh, I'm just going to move this to the other side of the equation and stuff like that. I don't know how much of it is really fundamental or if it's just that it's really easier to work with mathematically. So notice you training, your input and your output during training are always the same domain. Right? If I put in a cylinder, I get a cylinder out. I put in a sphere, I get a sphere out. So what we're doing here is actually something weird. I'm putting in a cylinder, but I'm getting a sphere out. That's the counterfactual. I'm switching worlds, even though I've never seen that in the training domain. I've never, started with a cylinder and produced a sphere.
Can you use something like a DDIB or something with fusion?
I think you can, but I think the problem is it the right match? And I'll show you an example. So I think DDIB has the same problem as these baselines here. I don't think it's fundamentally any different. So what does it do? This is basically when you assume just independent VAEs. I train an independent VAE and I just, for each of the domains, completely independently. I train a sphere one, I train a cylinder one, etc. And then I just encode with one and decode with the other. That's a little bit like DDIB, except it's a diffusion-based version. So what happens is it does correctly produce usually you're changing shape here. So it does correctly produce a bunch of cubes and cylinders, but what it doesn't do is it doesn't preserve the original. So this originally had a red background. This one is a reconstruction, so you need to look at the other ones. It doesn't preserve the background colors. So I only want to change the shape, but I'm actually changing the other colors. If you look at more like our method here though, right? I take a square and I can change it to a cylinder or a sphere. Now in this case, it messed up, right? So there is still some error. That's why there's that bound. We can't be perfect. But we're able to much more preserve the information from the original factual thing and only change the domain thing, which is shape in this example. You also find that if you use, you don't use enforced sparsity like we had, you end up where you're kind of off when you switch worlds, you end up in a space that it wasn't trained on. Because it's not actually Gaussian in the VAE case, right? It's some latent marginal posterior distribution that's regularized towards a Gaussian, but not exactly Gaussian. So when you switch spaces, you might be in a space that this other, the cylinder was encoded and it gives you some noise value. You move that into the sphere space and that sphere space is empty there. And that's why you get some like kind of garbage samples. So here you're kind of changing things more minimally and you are actually able to get this. Here's some other results, some more quantitative results, but I think I'll just leave it at that. Hopefully I've convinced you domain counterfactuals can be useful. Estimating domain counterfactuals as well as using it for robustness and stuff. I hope you are inspired to think about these problems. And that's it.
Urge to talk. Any questions? Other questions? Yeah, I think I also ask plenty of questions if we can wrap.
Yep. Sorry for going over.
Thank you.
have time, I actually would like to ask you some questions about another one of your papers. Sure, is it okay?
Anybody? Cookies, there's a lot left over.
I'm
Oh, please do.
Yeah.
Eat more than one.
So,
Eat
I do.
something. Or friends or whoever's at home. Oh, thank you.
At some point, we'll get on right now, because I want to ask you two questions.
Yeah, sure.
Yeah.
Are you busy back at 5?
Very last paper.
Oh, I think that's
Okay.
for domain estimating main It's characterizing domain counterfactuals. Or
Anyway, thank you. I've read it a lot. Thank you. What's your name? I'm Robert J.
oh, nice to meet you. Yeah.
Are you headed somewhere? If so, I can walk with you. I don't want to keep you away from what you did.
I don't know. Jing, are we going somewhere?
Yes, we could go around 5, to dinner before you go back.
Okay. Yeah, so I have a few minutes, I think, right? Or should we?
Yeah,
should we
I
start
think,
walking?
we can go at 5.
Okay.
Yeah.
Yeah.
Okay.
Minutes, sure.
Yeah, so my questions are on deep density.
Okay.
Why is that funny?
Oh, it's just, it's,
Yeah.
it's been a long time since I
Like,
directly worked on that.
linear.
Oh. Yeah.
Right, right, so it's like a classic tax, but
Yeah, so I have a couple questions. One, I guess, is not. So, but I'm wondering, like, this in principle sounds similar to the idea of diffusion models, but my understanding is that this came before diffusion models. So someone, what in your mind is sort of
I know is that
it seems to be basically the same thing. You just start with, you assume the uniform distribution, diffusion models assume Gaussian distribution, and then you're using some model, some series of models to map one distribution. To map the structure process, then you can reverse it because it's by checking. Distribution. So, I don't know, I'm wondering, do you have any thoughts as to functional differences, or if they seem basically equivalent with different.
So maybe I'll bridge it slightly, so. Flow-based models.
Right.
Do you know about flow-based models, right? So this the deep density structure in some ways was just a different algorithm for learning a flow-based model than using end-to-end backpropagation.
Right.
Flow-based models.
My understanding is flow-based models are one step, is that not true? Like one step from the data to the random distribution, or is that?
Well, it depends on what you define as a step. So most flow models have multiple layers. So it
Right.
depends on if you
I
think
see.
of those as multiple steps. So this was,
Okay.
in some ways, they would put, let's say, 10 or 20 layers together, let's do gradient descent, learn all 10 layers together.
Right.
In some ways, this work was something like, well, what if we did one layer at a time and used kind of classical ways of estimating distributions to kind of learn one layer at a time in a kind of greedy fashion, as opposed
I
to
see.
doing it jointly. So The good part. So that's just in relation to flows.
Right.
Right, so basically it's like learning layers. You could possibly, you could think about learning a little bit different kinds of layers, but at the end of the day, there, even like the tree-based one, I think is equivalent to some sort of Rayleigh network probably. So it's really a greedy way.
Right.
So I probably, it's mainly a different algorithm for learning flows. Now, now the question is, so what's the difference between flow and a diffusion model?
Well, my understanding is that, so the reason I connected this to diffusion is because the diffusion model, you're learning, the idea is you learn one model for every step of the noising process, and then they parameterize the model instead to save space, whereas you're actually learning one model for every step of the diffusion process.
Yeah,
That was my thought.
there's a couple other key differences, which are like, so one is that they move to the stochastic situation, where now you can think it's closer to an autoencoder. So a VAE, you can think of as a relaxation of the flow. It's now not perfectly invertible, so then you use the elbow, but that approximates, basically as the noise goes to zero, it's essentially the same thing as the flow model. So a VAE, you can think of the flow model as strict invertibility. VAE has like kind of relaxes the flow. Then when you go from VAE to diffusion, the difference is the encoder is fixed, the diffusion model. You just add noise, that's like a decoder, but it's like a very simple, encoder. A very simple encoder, and all you're learning is decode.
I see, yeah.
It turns out, so flow models essentially learn both at the same time.
Right, yeah.
But the problem, at least like with this greedy approach, is that the greedy approach has a problem, I think, because it's greedy and it's not global. And so that's why I've kind of started to steer away from the greedy approach, because global dot propagation just almost always wins. But I am still interested in the localized learning type of problems. But under different scenarios.
Yeah, I guess my main interest with your paper is, so I'm interested in sort of the idea of copula models, and you mentioned in your paper that in some way it can be interpreted similar to a copula model, except instead of interpreted similar to a CDF where you map to the unit interval, except in this case you're mapping to the unit Q because it's an invertible. And then you say that it's similar to a copula in that way, that you have the you map to the hypercube, but it's not necessarily. So my interesting copula is like you have access to the models with marginal distributions already. Univariate margins. Then you combine them using another model. Does your method have any relationship to this interpretation of a copula, or are you referring more to univariate marginals? Sorry, I mean the hypercube,
So if you first model the marginal,
我得看一看，
you do one layer of that.
我刚才跟他说了，能说了是吧？听了我忘了，29号，下周fall break 大家都出去玩了，
对，都没人了，
算了，看漏了，
对，就看着。
Yeah, I'm trying to think of what the connection was. As soon as you remove the marginal information, then you're just doing the
archival.
Right.
Right. Then you're just destroying the non-marginal information essentially. I don't know.
I think so. So I guess my question is would you think you would be able to formulate this as a copula? Like, say you have two images or whatever, you train your model on each of them, so you get so you basically destroy all the information in each image individually, and then you train another model on sort of that destroyed information to further remove the information. That would be kind of like a copula. You have one model for like, I don't know, images of people, one for like images of dogs, and then you train them each individually. And then you train another model to remove the joint information from them, assuming that it's like a picture of a person. You've got a picture.
Right.
So that approach, you could do something like that using your method, and that would be more like copula, I guess.
Yeah, I mean, maybe you're thinking of defined copulas.
I've heard of the Vine copulas,
It's weird, crazy.
Yeah, they're-
statistical construction.
I haven't looked into them too much. My understanding is it's kind of like autoregression, but like in terms of like variables or something on copulas. But
Yeah, it's been a while since I've done random copulas. But
My thought
yeah,
is more
the
like
hierarchical copula, I thought about doing that. And I've always been intrigued by it, but then I'm like, it's never really. So,
yeah, well, my thought is more like model reuse, like you can kind of mix and match models.
yeah, I would say the problem with that is you should just use the diffusion model. Because diffusion model has a unique solution. Basically, given a set of samples in a diffusion. Theoretically, you're not exactly one solution.
Okay,
In my case, with density structure stuff, there's many possible solutions. And that can be bad, and that's part of the reason diffusion models actually work. One of the reasons they work is because they're so stable. Basically, there's only one such mapping from any distribution to a Gaussian. Now, of course, if you have a Gaussian, you can just convert it to a.
right,
So no fundamental. Except in popular models, some people care a lot about tail behaviors. If you're dealing with thin tail, like thick tails that are not like sub-Gaussian type tails, then you need to do things. Like people show like flow models can't. ReLU flow models with like a Gaussian prior can model heavy tails. If you don't care about tail behavior, then you should probably just, you could possibly do something similar, but just the question is whether hierarchical diffusion would allow you to do this. But I think it's totally reasonable to think two separate models and a few joint samples, let's say.
Right, yeah.
Kind of do another diffusion model, after having used a lot of information from individual things.
yeah, that's exactly
So I
our
would
setting.
probably, I would recommend it.
Okay, yeah, that's where we were going, and then I found this paper today, and so I thought, I would like to hear your perspective on it, but it seems your suggestion is that you like diffusion models in this setting that you described, which is our setting.
If you have a good pair of examples, you have a bunch of things, trying to share knowledge. Yes, that would be my first. Yes, he probably doesn't. And the only reason to do localized learning is when you're distributed. Otherwise, if you have centralized.
Yeah, basically our motivation. So we do like design like that. So basically the idea is like individual proteins, but not a lot about protein complexes. So you can kind of treat that as you got proteins that are your protein complex is the joint. You can try to use like a little bit of information to like correct for this. Yeah, to make a correction to the product distribution, basically. That's the general.
There might be other ways to do transfer learning. So I haven't thought about it. I'm not sure.
We've thought about it. There are a couple ways you can do it. Diffusion models is one I was going to, but I just wanted your.
Yeah.
Thank you very much.
Yeah.
Glad to know that you created diffusion models. Probably the way to go towards.
Yeah.
是你懂做分析的人可以
Really
懂，那很多不做分析的人，因为你指导人控制不了，要做实验的。 因为你天天搞这理
You're
论，
not
我根本
like
不会用
the。counterfactual case, I
对
think
对
is
没用，没意义，看了开喷，一点怕没有，
but
你解释不了，的确你用的是
you need to learn
那
it
你就
later.
只能说你放
It
该
doesn't allow you
命
to
啊
learn
这些话
how to turn
都
around.
直接
It's
就
good
直接
because
别
it's
套
a unique representation. It's bad because you can't learn an arbitrary, like you can't use it to learn it. But some people use, anyways,
就那个
so the stability of it is really good.
Right.
And that's what
I'm
makes
I'm
it.
three 我也投
Okay, do you work
那
with
种
fusion models?
43
much?
Yeah, I do some, yeah.
Okay, if I have more questions about this, like fusion populist stuff, do you mind if I email you if I have like some questions?
Yeah.
Okay, thank you.
好像就1、2、3、4，对，就5分，我也投了嘛，我们有一个文章也是在3。
like I have two sets of images. One set is humans.
Right now?
Yeah.
Okay, yeah, we can.
Pictures.
也行
Humans in
Yes,
in the
yeah,
city.
yeah.
Yeah. So
What group are you in?
there are some humans. Okay. And we want to transfer
Okay.
the picture from random.
You supervise a lot
Can we
of
use
students.
your method to
Yeah.
transform it?
Everyone I do.
Just like
Like you-
generate the
Big group.
factor example.
Yeah, we haven't done it on a large scale yet. Not actually on a large scale. So it's a little unclear whether we've done online.
There we go.
Like, I don't know what it is, let's say.
I think maybe we really need to I have another question is that in the real data set, how do you find the causal relation between the x, y, and some other latent variables? Yeah, I think you generate the counterfactual examples based on the causal relation, right? And so if we want to generate counterfactual examples on a real data set, we need to find the causal relationship.
Well, so it depends on which work you're talking about, so the counterfactual fit and the estimating counterfactuals, they were assuming you don't have access to the counterfactuals.
Yeah.
Meaning, so you have to estimate them.
Yeah, yes.
And estimating them, as we showed, is hard. But under some assumptions, it's possible. And how far can we go? I don't know empirically how far we can go yet on. Okay, basically you need some data. If the, at least domain data, we think is at least, which people think of as unknown interventions. We need at least that, and is that enough? You say, well, not quite, but maybe under some additional things. So I would say, like, can you do it without? The thing is you don't necessarily have to know the causal model. We're not assuming you know the causal model.
Oh,
You're just given data.
okay.
In all these cases, you're just given, well, yeah, most of them we're assuming you just give them data. So you're either given, in the domain generalization case, I'm assuming you're given some counterfactual pairs, but you don't know the model. If you knew the true causal model, you could do all sorts of stuff. That's really hard
Yeah.
and takes either a huge amount of data or like oracle knowledge. So we're trying to say, what can you do if you're given not the causal model, but just these counterfactual pairs, just some special data?
Yeah.
Then can you do something and what kind of things can you do there?
Oh, okay.
But we're also wondering, can you estimate these? So under some assumptions, you can estimate. And maybe that could be enough sometimes. But those, of course, will depend on assumptions. So a lot of causality is based on you take data plus some assumption. When and if does that assumption hold? Could you have a hope that actually?
Oh, okay, I get it.
But otherwise, it might work in your application by coincidence, like CycleGAN, StarGAN. Those, I think, work by coincidence. They're not actually grounded in, they're not producing kind of real counterfactuals. They're producing something that looks nice. And maybe that's enough for your application, but if you want to do something more careful, you can't necessarily
Okay.
hope for the best, which is what a lot of machine learning is.
Thank you.
Yeah,
Thank you very much.